Hello, today I'll be going through Lewis structures, resonance structures, and formal charge. Let's start with CHO2 minus. Usually I start by counting how many valence electrons there are so that I know what the Lewis diagram is supposed to look like. So carbon has 4 valence electrons, hydrogen has 1, and there's 2 oxygens, so 6 each times 2 oxygen atoms. And then this negative sign means that there's 1 extra electron. So in total we have 18 valence electrons. So to draw the Lewis diagram, you want to take the atom with the most possible bonding electrons, which in this case is carbon. In most molecules, if you see a carbon, it's usually the central atom. And then you can draw 4 dots around it because that's the number of valence electrons it has. And then we can take the oxygens and let's take the hydrogen first, because hydrogen we know has 1 valence electron and that bonds to 1 of the electrons in carbon, so that makes a single bond. And then O2 let's draw 1 on each side, and each one has 6. So 1, 2, 3, 4, 5, 6. And then this one also. 1, 2, 3, 4, 5, 6. Okay, so now what we have left is 3 possible bonding electrons on carbon, but we have 4 singular bonding electrons on these oxygens. So there's an uneven pairing number. And what we do here is we can double bond oxygen with one of them, because oxygen wants to make as many double bonds as it can, whenever possible. But now this one can only single bond with this carbon. So what we want to do is we can take this extra electron that comes from our -1 charge and add it onto this O, because it's like full valence electrons, right? So this now has 1, 2, 3, 4, 5, 6, 7, 8. So now it has a full valence shell, and we also incorporated our 18 total electrons. So let me count it out real quick. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And let me redraw our Lewis diagram really quick. So the hydrogen is single bonded to the carbon, and the carbon's double bonded to this oxygen, which has 2 lone pairs, and single bonded to this other oxygen, which has 3 lone pairs. One more thing I forgot to add is that we have to add brackets around this entire Lewis structure and draw a negative sign at the top right corner to indicate that this entire molecule has a -1 charge. So since this molecule has a double bonded O and another single bonded O, then we can draw a resonance structure for that. And we can start by doing the central atom and the H again, because those can't change. But this time we just switch where the double bond is. So in the first diagram, the double bond is on the left, but now we can just draw the double bonded O on the right of the C. And then the same valence electrons should apply for each. So double bonded will have 2 lone pairs, while the single bonded has 3 lone pairs and 1 extra electron right here. And then we do the same thing, draw brackets around, and the negative sign. Last, let's calculate the formal charges of each resonance structure. Formal charge is basically the individual charges of each atom inside the molecule, and they help determine which Lewis structure, which bonding way, is the most accurate. So the equation for finding the formal charge of an atom is the number of valence electrons minus the number of lone electrons minus the number of bonds. Let's start with the diagram on the left. So carbon has a total of 0 lone electrons and 1, 2, 3, 4 connected bonds. So we would take the valence electrons, which is 4, minus 4 bonds equals a formal charge of 0. Now hydrogen has a total of 1 valence electron and also the total of 1 bond connected to it. So we would take 1 valence electron minus 1 bond equals 0. So once again, this one has a formal charge of 0. And now for the oxygens, there are actually 2 oxygens, which is the oxygen that's double bonded, which I'll say is OD, and the oxygen that's single bonded, which is OS. We know that every oxygen atom has a total of 6 valence electrons, so let's write that first. And let's first look at the double bonded oxygen. So for lone electrons, it has a total of 1, 2, 3, 4 lone electrons, because you're counting each individual dot that you see. So minus 4, and then it also has 2 bonds, which is -2. So 6 minus 4 minus 2 equals 0. Now for the single bonded oxygen, let's count how many lone pairs it has, lone electrons, sorry. 1, 2, 3, 4, 5, 6. So -6, and then it has 1 bond. So that means -1, and it has a total of -1 for its formal charge, and that is where this negative comes from for the entire molecule. This is because of the single bonded O's negative formal charge. Now for this diagram on the right, since these are resonance structures that only flip-flop the 2 oxygens, they're the same atom. So they technically have the same formal charge, except this single bond would be this one, and this double bond would be this one right here. Since these two structures have the same formal charge, that means that these two resonance structures are equally scientifically accurate. Here is an example of a molecule that has no total net molecular charge, but has different formal charges. So SO2, you would start by drawing an S in the middle, and it has 6 valence electrons. So you could draw it like this because that's how they would bond, like linearly. And the O2s would be on these two sides, and they would have 6 valence electrons each as well. So SO2 actually has 3 different resonance structures, and the first one is, if you couldn't tell, like, let me connect. It would be like double bonded to, the S would be double bonded to the oxygens on both sides, and it would look like this. Now, there are 2 other ways that you can draw SO2, and these 2 are similar to each other. Okay, I just set up these 2 with the valence electrons, and let's focus on this one. You can single bond this right here, and then actually double bond this right here, right? And then you have this extra electron at the bottom, which you can move here to complete its, or to pair up its single electron into a lone pair. And for the third resonance structure, it's basically the same thing, just flip the location of the double bond. So the double bond would be on the left, and then you move this electron instead to the right oxygen to make this one single bonded and the left one double bonded. I just rewrote these 2 resonance structures, and now we draw the arrows. Now that we have our resonance structures, we want to find the formal charges of each resonance structure. Let's start with the sulfur. So sulfur has a total of 6 valence electrons, so I'm going to write that for all of them. And then for the first resonance structure, it has 2 lone electrons minus 4 bonds, and that equals 0. Now for the oxygens, since this first resonance structure only has double bonded oxygens, then they should be the same, but I'll just write D right here. And each oxygen has 6 valence electrons again, minus 4 lone electrons and minus 2 bonds, and that equals 0 again. For the second structure, we have 6 minus the 2 lone electrons minus 3 bonds this time, which equals positive 1, and that means that this sulfur has a formal charge of plus 1. This structure also has 1 double bonded O, but it's not both of them, so we also need to do both of the O's separately. So let's do the double bonded O first. So 6 minus 4 lone electrons minus 2 bonds equals 0. Now for the single bonded electron, or single bonded oxygen, let's write another column for that. It has, again, 6 valence electrons minus 6 lone electrons this time, because they have 1, 2, 3, 4, 5, 6, and minus 1 extra bond, which equals negative 1. So this oxygen has a negative 1 charge, formal charge. Also, we can check if our calculations are correct by looking at the formal charges and then seeing if they add up to what this molecule's net charge is, which in this case is 0, and this is correct. Now, last but not least, this sulfur, the third sulfur, has 2 lone electrons minus 3 bonds equals plus 1 again, so this has a positive 1 formal charge again, and the double bonded oxygen has 6 minus 4 minus 2 equals 0, single bonded has 6 minus 6 minus 1 equals negative 1, and it has a negative charge right here because this is a single bonded oxygen this time. So therefore, we can see that the very first resonance structure has the least amount of formal charges, because they're all 0, and we want that. So this resonance structure is the most scientifically accurate.